In this video, we'll discuss two phenomena that we observe with sound waves, the Doppler effect and beats. Let's start with the Doppler effect. You may have noticed the tone, which is to say the frequency, of an ambulance siren changing when it passes you. In just a moment, I'll show you a video of this happening. In the video, there are two frequencies emitted by the ambulance. Notice that the frequencies are higher as the ambulance approaches the person filming. We'll call that person the observer. And the frequencies are lower as the ambulance passes and the ambulance moves away from the person. Here's the video. A change in the frequency like this that an observer hears is called the Doppler effect. There are two scenarios that produce this effect. One is when the observer is stationary and the source of the sound is moving, which is the scenario we just observed in the video. And the other scenario is when the source is stationary and the observer is moving. Here's a simulation to demonstrate how both of these effects occur. This simulation actually demonstrates the Doppler effect for light waves, but the effect is identical for sound waves, so I'll use it for that purpose. Therefore, in the simulation, we'll say that this is not space, but rather everything is surrounded by air, so there can be sound waves. The star will be the source of the sound waves, and a person in the ship will be the observer who hears the sound waves. The sound waves that the observer hears are in the lower left corner of the simulation. Notice the approximate frequency of those waves right now, because the frequency will increase and decrease as we go through the simulation. In the simulation, I'll now cause the ship and therefore the observer to move towards the star. Notice the observed frequency in the lower left increases because the observer is moving into the waves, causing the perception of a higher frequency. And now, after the ship passes the star, it's moving away from the source. Notice that the observed frequency now decreases because the observer is moving with the waves, causing the perception of a lower frequency. Now I'll change the simulation so that the observer is motionless and the source, the star, is moving toward the observer. This is the scenario we saw in the video with the ambulance. Notice how the wave crests are compressed in the front of the star and are spaced out behind the star. When the compressed waves reach the spaceship, the observed frequency increases. And now when the star passes the spaceship, the frequency decreases. So let's summarize what we saw in the simulation. The observed frequency increases if either the observer moves toward the source or the source moves toward the observer, and the observed frequency decreases if either the observer moves away from the source or the source moves away from the observer. And these results are expressed by this equation, where f0 is the frequency perceived by the observer, fs is the frequency emitted by the source, v with no subscript is the speed of sound in the medium, v0 is the speed of the observer, and v sub s is the speed of the source. This equation is actually an approximation. The error gets larger as the speed of the observer or the source gets closer to the speed of sound in the medium, but for this course, we will not have to worry about this error. In the equation, notice the plus minus in the numerator and the minus plus in the denominator. The rule here is to use the signs on top when that object is moving toward the other object, or use the signs on the bottom when that object is moving away from the other object. Or we can just express the rule explicitly like this. If the observer is moving toward the source, then the numerator is v plus v0. Or if the observer is moving away from the source, then the numerator is v minus v0. Similarly, if the source is moving toward the observer, then the denominator is v minus vs, so it's minus this time. Or if the source is moving away from the observer, then the denominator is v plus vs. And there's a worked out example that's posted to demonstrate the use of this equation. Related to the Doppler effect is another effect called a sonic boom. A sonic boom occurs when the source is moving at the speed of sound in the medium. I'll use the previous simulation again to demonstrate this. I'll make the star, which is the source of the sound waves, move toward the observer at the speed of sound. As this happens, notice that all the sound waves in the front are combined, or they're very close to each other. When these combined waves reach the observer, the result is a very intense wave that's perceived as a loud boom that we call a sonic boom. As a matter of terminology, if an object is traveling at the speed of sound, then we say it is traveling at Mach 1. If it's traveling at twice the speed of sound, then we say it's traveling at Mach 2, and so on. The term Mach number is defined to be the speed of the source divided by the speed of sound. Now let's discuss the phenomenon called beats. Here's a video of the effect. Notice when each tuning fork is struck and plays by itself, we hear a tone around 250 Hz, and we don't hear anything unusual about it. But when both tuning forks are played at the same time, we hear a sound that goes up and down. What we're hearing is the intensity of the combined sound wave oscillating up and down, an effect we refer to as beats. Beats occur when two sounds with slightly different frequencies are played at the same time. So the tuning forks we just listened to had nearly the same frequency, but they were not exactly the same. So why does this happen? Say this is a sound wave of some frequency, and there is a second sound wave of the same frequency exactly in phase with this one, so that it's behind it and we can't see it in the plot. The superposition of these two waves would then be this wave, which is what we hear. Now let's say the second sound wave has a slightly smaller frequency, so the two individual sound waves look like this. The superposition of these two waves is this wave. As you can see, the amplitude of the superposition wave decreases over time. If the frequency of the second sound wave is decreased a little bit more, then the superposition wave looks like this. So the amplitude of the superposition wave decreases more rapidly this time. Note that it doesn't matter if we had increased or decreased the frequency of the second sound wave from the original frequency. We get this effect because there's a difference in the two frequencies. Now I'll increase the time scale so that we can see many more cycles of these sound waves and get a better understanding of the effect. Here are the two sound waves with a difference in frequency of, say, 1 Hz. And here's the superposition of these two sound waves. This superposition is what we hear. So the sound is initially loud, then quiet, and then loud again. This then would be one of the beats we heard with the tuning forks. Now I'll change the frequency of one of the waves so the difference is increased to 2 Hz. And we can see that another beat has been added to the plot. If we change one of the frequencies again so that now the difference in the frequencies is 3 Hz, we get another beat. And so it keeps going. Here's a difference of 4 Hz, and here's a difference of 5 Hz. To summarize then, the farther apart the frequencies of the two sound waves are, the greater the beat frequency is. And mathematically, the beat frequency is just the difference between the two sound wave frequencies. So it's a simple result in the end, but I think it's very interesting how it occurs. And so that brings us to the end of this video. In the next video, we'll discuss more interesting effects that occur when waves combine. See you then.